Stripping down science. The Naked Scientists.
Hello, welcome to this week's Naked Scientists. That's with me, Chris Smith, and also with Helen Skells, who's here this week. Hi, Helen.
Hello.
Now, coming up on this week's programme, how a man's iPod gave him an electrifying musical experience, and you'll be shocked to hear why. Why penguins are changing their diets. Also, how scientists have found for the first time water on a distant planet. And also how researchers have found a cunning way to turn waste sugar into a fuel that packs a similar punch to petrol.
Well, we came up with this compound called dimethylfuran, DMF. And it turns out the octane number is something like around 120, which is a very, very good octane. So dimethylfuran should be a very, very good burning fuel if you can make it efficiently from biomass.
And on the subject of fuels of the future, this week we're finding out how to power the next generation of cars and trucks, but without harming the environment. From the man who invented the first LED, we'll be hearing about a new way to produce hydrogen in large amounts, but much more safely than having a great big cylinder of it sitting in the back of your car. And for this week's Kitchen Science, we've sent Azzy to Bath University's chemistry department to find out how we make biodiesel. She'll also be having a go at testing what they make, so keep listening to find out whether it works or not.
And is all of this talk about environmentally friendly fuels actually scientifically sound? Should we be leaving things on standby? Is there a good basis for saying, let's turn them all off at the mains? Well, we'll be finding out from Peter Mackay later on in the programme. Plus, there's also this week's Question of the Week, which ought to raise a few eyebrows, if not a few hind legs.
Hi, my name is Michael Rashty. I'm calling to find out what dogs are doing when they're lifting their legs. Are they targeting a particular spot, aiming to cover up another dog set? And how do you know?
Sounds intriguing, but to answer that, wait a little bit and we'll have that coming up. But we also have this week's teaser question, which is, how many tons of prehistoric plant matter has gone into every gallon of petrol we burn? So how many tons of prehistoric plant matter and stuff that lived a long time ago does it take to make a gallon of petrol?
The Naked Scientists podcast, powered by UK Fast, the UK's best hosting provider. On the web at ukfast.net.
Now, interestingly, let's kick off with an electrifying experience for someone. This paper in this week's New England Journal of Medicine, Helen, in which this guy was jogging along in the rain and in the thunder, and he was listening to some music on his iPod. And he unfortunately was a victim of a thunderclap. It jumped onto a tree nearby him, and then this side flash meant the lightning came off the tree and hit him. And at first, doctors were a bit confused as to what had happened to this guy when he pitched up in hospital, because witnesses said he jumped about 8 feet across the road, but they didn't know why. When the doctors examined him, he had burns on his chest. He then had 2 straight line burns going straight up his chest, up the side of his neck, across the side of his face, and ending in his ear holes. When they looked in his ears, both his eardrums had been burst, they'd been ruptured, there was blood coming out. And what had happened was he then was able to say, well, I was running along, I was listening to my iPod, and suddenly I found myself on the ground with a broken jaw and all these injuries. And it turns out the thunder had jumped off this tree and onto him. Because of the metal in the wires, it had gone up the headphone lead, making it very hot in the process and burning him, and then into his ears, and it had superheated the air in his ear canals and made it expand, which had popped his eardrums. And so there's, although Eric Heffernan and his colleagues who wrote this paper in the New England Journal say that iPods are not a risk factor for being hit by lightning, they don't want to get sued, obviously. What they are saying is be careful when you're out in thunderstorms with electrical apparatus, because it can make this happen.
Do you think that really was the reason why it jumped across to him and it wouldn't have done that anyway? I mean, he might have been hit anyway, but just in a slightly odd way and with his eardrums.
No, most people who get hit by lightning, actually under these circumstances, it is exactly that. It's lightning hitting something else and then jumping off of that onto you because you provide an additional or alternative route to ground for the electricity. People are speculating about what he might have been listening to on the iPod at the time. Any suggestions?
Do you know, I've no idea.
Pink Floyd, Delicate Sound of Thunder. That's my suggestion.
Excellent. Yeah, I was caught in the rain big time this afternoon, but luckily I wasn't listening to any music. Anyway, I'm going to take our news stories a bit further south now with a story that penguins living in the Antarctic have changed their minds about their favourite food, and a change of diet that could have been triggered by the hunting of whales and seals over the last 200 years. Now, you might think that an obvious way to find out what a penguin has been eating would be to have a look inside its stomach, but that's only useful, of course, if your penguin is still alive. survive. But luckily, penguins live up to that old cliche of you are what you eat, because they leave behind traces of what they ate in their eggshells that they lay and in their feathers and their bones.
When you say traces, is that like a chemical fingerprint then?
Yes, that's right. It's a chemical fingerprint that we're looking at. And in fact, it's a balance of two compounds or isotopes, if you like, called carbon-13 and nitrogen-15. Now, these both occur naturally in the environment, but in different ratios in different types of animals. And that's the key to this question that Stephen Emsley and William Patterson from the United States were setting about to investigate in the diets of Adelie penguins, which live around the Antarctic continent. And they took eggs and feather samples from both modern-day penguins and the fossilised remains of penguins that lived up to 38,000 years ago.
So how's it changed?
So what happens is they're looking at this ratio of C13 to N15, and that basically has, it's gone up, I think. Is that the right way around? Yes. It turns out that the ancient fossil penguins had isotope ratios that hinted at their diet being mainly made of fish, because that's the kind of signature, if you like, that you see if you look at a fish. And that's different to what you might see if you looked at krill, kind of a type of crustacean. Those are those little shrimp-like creatures that fill the cold oceans.
So the penguins have changed from eating one thing to eating another.
So basically we see that they were predominantly eating fish, it seems, before, but very recently modern penguins seem to have flipped their diet and are eating krill.
When you say modern, how recent is this?
I think it's in the last 100 years.
So could that be us? Is that because we're depleting the oceans of fish so they're having to eat something different?
I think it's two things. Partly it's the fish are going down because we're starting to fish the fish that live in the Southern Ocean, things like Patagonian toothfish and stuff like that. But it's also that for hundreds of years we've been hunting the whales and seals, which are naturally the predators of the krill. And there is this phenomenon that we are seeing more krill being more abundant in the Southern Ocean.
So there's more krill, so the penguins are thinking, rather than go for the fish, which is difficult, I'll go for the krill.
And that's quite good. That is, it's obviously a sensible thing for them to do. The problem is now, we've also noticed that there are more krill, and there's plans afoot to start fishing them ourselves. And do you know why? Because we don't actually eat krill ourselves. I don't think they're very tasty for humans, but they are good for those fish that we grow in farms.
Oh, of course.
So we make them into fish meal, and that's the plan, which could be a problem if we start then competing with the penguins for the food that they prefer now, and there may not even be enough fish for them to switch back to fish. So
is there any evidence that the penguins are worse off eating the krill?
I don't think so. No, I think they're fine. I think they're doing okay. But as long as we don't start pitching too much of their krill...
Upset the apple cart even more.
Yeah, indeed.
Well, that's a wet story. Here's another one, but not on this planet, because for the first time scientists, Helen, have managed to find water on a planet outside our own solar system. They've looked at a planet called HD 189733b. It's actually 60 light years away. It's a long way. You won't find life there either. It's a sizzling 1200 degrees Celsius because it's very, very close to the parent star. It's a Jupiter-sized planet, about 15% larger than Jupiter, but it's a wet place apparently too. Giovanna Tinetti, who's at University College London, has just published a paper in Nature this week where they watched with the Spitzer Space Telescope this planet going round and round its parent star, which it does every 2 days. And what they could do is compare when the planet goes in front of the star, and then what you see is the starlight coming through the atmosphere of the planet, with when the planet's gone away again, you can just look at the starlight, and because different chemicals soak up different wavelengths of light in a very characteristic way, you can use this to work out what must be in the atmosphere because it's soaking up certain wavelengths of light. So they find the specific fingerprint for water in the atmosphere of this planet, and this shows that we can now do this, so we should be able to use it to track down planets that are wet, maybe like the Earth, in future.
Sounds great. Now back down to earth, because I have good news this week for lovers of muck and magic, because it seems that organic farming could actually be capable of producing enough food to feed the world. That's according to a study from a team of researchers led by Yvette Perfecto from the University of Michigan in the United States. Now what they've done is they've pulled together a huge amount of data on farming productivity from the United Nations Food and Agricultural Organization, or the FAO, and their findings fly in the face of what's widely believed is the fact that organic farming won't be a global solution to feeding the world.
Because it's just not productive enough.
Because
it's
extensive. That's the key to it. We're not talking about intensive farming methods, so maybe we just assume that organic farming is not going to work. But actually what they found is that in developed countries, organic farms can produce about 92% of the food that conventional farms can generate. But the really good news is that in developing countries, it could be up to actually 80% more food is produced on organic farms compared to conventional farming techniques.
But why should we have got it wrong? Why should we have thought it wasn't possible, and now you're saying that people think we can?
I think it's probably because we haven't looked carefully enough at the question. We have just, I think, maybe looked at small case studies and what they've done is taken a real global view in different countries as well, and, not just on our own doorsteps but globally. And I think, looking more carefully and in more detail at the question, you come with maybe a different picture to the question we're looking at. We don't know this for sure yet, but it's certainly an interesting possibility that...
So the bottom line is that we're going to have to say to farmers, you can't use all these chemicals because there's now scientific evidence that you can farm organically and as productively as existing methods.
Well, I mean, that's certainly one
have
thing
some friends
you
in the farming community out there, aren't we?
I think it's more a case that we can ride on the kind of popularity of organic farming, not only in this country, but it's something I think that's going to be really important in developing countries because they can produce their own fertilisers. I think the problem is they normally just can't afford the fertilisers and pesticides that we are using a lot in the developed world. And if small farms can produce more food and have more food security, that's got to be a good thing, surely.
Well, let's hope so. I guess we'll have to watch this space and find out whether or not the promise of organic really can pay off. Well, finally this week, a really heartening story for people that are interested in the field of cancer and cancer research, because there is a group of researchers at the University of New Mexico, and they've teamed up with a company called Senior Scientific, also in the US, and they're looking at ways of doing better biopsies. Now, when you do a biopsy, what you're aiming to do is to stick a very fine needle into what you think might be a cancer to get some of the cells out so that you can study them down a microscope and confirm whether or not something is cancer. But if you've only got the odd rare cancer cell there, sometimes you can miss it, and prostate cancer is often falls into this. This is what happens with prostate. You can miss some of the tumour deposits, and so you can get a false negative diagnosis. What these guys have done is to come up with an idea of a magnetic nanoparticle. So you can inject these particles. They are iron oxide, which is, of course, magnetic, surrounded by a biocompatible material to which you can link antibodies, which will lock that nanoparticle onto the surface of certain cancers. This makes the cancer cells become magnetic, and then you go in with a needle, which you can apply a magnet to, and this makes the needle magnetic and sticky, so it will soak up the cancer cells, and you can get much more or increased chances of getting a positive biopsy out of it.
And how does the sorry, Chris, I was going to just ask you how do the those iron particles know to only stick to the cancer cells?
Because you can glue to the outside antibodies which will recognise specific markers that are only expressed on the cancer cells, and this means you can make them only congregate on the cancers, nowhere else, so you only pick up cancer cells, or that's the hope.
The Naked Scientists, supported by the Wellcome Trust.
Now, you might have heard recently that a well-known fast food chain have decided to start converting all of their waste cooking oil into biodiesel to power their fleet. Well, to do this, they need to filter the oil and refine it to get clean oil, but by doing so, they've claimed that they can reduce their carbon dioxide output by the equivalent of taking 2,424 family cars off the road. So we sent Azzy Katiri to Bath University, or should that be Bath, to find out about one way in which you can convert clean oil into usable biodiesel. Hi, Azzy.
Hello, welcome to Kitchen Science. This week I've come to the historic city of Bath, and I'm actually standing at the University of Bath's chemistry department. I'm joined by Professor Davidson.
Hello.
And also Christopher Chuck, who's a PhD student here.
Hiya.
The question I've come to you guys with, and I'm really hoping you can help me out here, is can you run your car on cooking vegetable oil?
That's an interesting question as to whether you can run your car on vegetable oil, what's chemically called a triglyceride, which is a molecule with 3 long fatty arms on it. And what happens is they all simply just get entangled together, and that means it has a very high melting point. The 2 most important problems are, firstly, the stuff would freeze in your tank, so on a slightly cold morning you would have a solid mess. And the second problem is that it simply doesn't burn very well.
Okay, so what's the solution?
Well, the solution is actually quite simple chemical process, and I can show you exactly how we do it. But before I do, I want you to put on some goggles just to make sure we're safe.
Okay, I've got my goggles on.
Right, well, what we're going to do is we're just going to take some vegetable oil that we bought at the supermarket, and we're going to take this mixture here, which is methanol and sodium hydroxide, and we're just going to mix it with vegetable oil, and you can see that the vegetable oil is stirring away with a stirrer in it, and it's heated up to about 60 or 70 degrees centigrade.
Okay, so you've got the vegetable oil in a flask, and you're putting sodium hydroxide, which is mixed with methanol, in the measuring cylinder, and you're going to tip it in.
Yep. We need to wait about half an hour, and what we'll see is the separate components. The biodiesel will separate out from the byproduct, which is called glycerol, which is the other part of the fatty molecule that we started off with.
So what's the chemical process that is happening inside that flask?
Well, the chemical process is something called transesterification, which is a bit of a complicated term for simply just changing the end of the long fatty molecule. So instead of having 3 of the fatty molecules attached to one end, a bit like a piano stool with 3 legs, we're changing the end and we're just capping off the end of the fatty molecule with the methanol. And that gives us individual fatty molecules, and that's what is actually called biodiesel that we could use in an engine. And another molecule called glycerol, which is actually a waste product of the biodiesel process.
Well, that sounds incredibly straightforward to me. Is this something that you could perhaps do to any old oil?
Well, yes, it is straightforward, but of course nothing's quite that simple. And I'm going to hand you over to Chris now. He's going to show you why it can't work on just any old vegetable oil.
Yeah, that's right. You have to use absolutely pure virgin vegetable oil. If you use waste oils, the kind of oils you cook your chips in and things, because you've heated it up to really high temperatures with food in, you might have bits of chips, bits of organic matter, and you'll have water, but most importantly, you'll have free fatty acids, which are the acid versions of those arms. And as soon as the sodium catalyst comes in contact with those free fatty acid arms, it just makes soap and no biodiesel whatsoever.
Oh, you can't really run your car in soap, can you?
No, you can't run your car in soap. There's at least 3 or 4 different purification steps that you have to do first to get your waste oil ready to make biodiesel from, which is very expensive to do.
All right, well, we've got half an hour to wait before our vegetable oil is turned into biodiesel. So we'll be back later on in the programme to show you what happens. Back to you guys.
Thank you very much, Azzy. Well, we'll be going back to Bath to join Azzy later. Hopefully she'll have some biodiesel made for us by then we can test it out in a car. We're volunteering the BBC's radio car.
And now it's time to go skipping across the Atlantic for the Science Update team. Bob Hershon and Chelsea Wald are waiting for us. Hi, guys.
This week for The Naked Scientists, I'm going to talk about a possible source of energy that has scientists all abuzz. But first, Chelsea's going to talk about the food that fueled one culture of the past.
If you could travel back in time to the Mexico of 1,000 years ago, the food would probably have a familiar kick to it. This according to archaeobotanist Linda Perry of the Smithsonian's Museum of Natural History. She and her colleagues discovered well-preserved scraps of domesticated chili peppers in an ancient Mexican shelter cave. The peppers date back 5 to 1,500 years. Perry was struck by the variety, 10 different kinds of peppers in all, including 7 in a single location.
Because you're not going to be growing 7 different kinds of peppers if you're not making some really interesting food.
What's more, she says the peppers appear to have been used in both fresh and dried forms, providing a broad spectrum of spices that could fuel dishes similar to today's Mexican specialties.
Thanks, Chelsea. Okay, cue the music.
I'm picking up good vibrations. She's giving me the excitations.
40 years ago, Good Vibrations were giving the Beach Boys excitations. Now, Steve Beebe of the University of Southampton in England is using vibrations to generate real electricity. He's developed devices as small as a sugar cube that you stick on any vibrating surface. The vibrations jiggle a few strategically placed magnets which surround a copper coil.
So the coil's stationary and the magnets are moving, and that way you build up an electromotive force in the coil, which is basically a voltage.
It's a low voltage, but Beebe says it's enough to run small wireless sensors that monitor the structural integrity of machines and bridges. And in theory, it could even power a battery-free pacemaker just from the pulse of a patient's heartbeat.
Thanks, Bob. We'll be back next time to talk about some surprising things some bugs and plants do to protect their families. Until then, I'm Chelsea Wald.
And I'm Bob Hershon for AAAS, the Science Society. Back to you, Naked Scientists.
Fantastic. And remember, if you want to check out more from the Science Update team, you can have a look at their website, www.scienceupdate.com.
It's The Naked Scientists with Dr. Chris and Dr. Helen. And this week we're talking about fuels of the future in just a second. And we're going to be finding out about lightning, because we'll be talking to Mike, who's in Beatley. He's got a question. I've also got an email from someone called... who wrote to me? Andy John wrote to me as well to say he wants to know about harnessing electricity and lightning. So that's coming up in a second. But first, Helen, there's one for you. Andreas Rice says, I'll be entering the 5th grade this year and I hope your programme can help me to understand science a little bit better. Got a question for you. Why, when I yawn, does it make tears come into my eyes?
OK, right. What the other thing you tend to do when you yawn is you screw your eyes up. And I think what that does essentially is put some pressure on your tear ducts, thus producing... No, on the the ducts behind your eyes that produce the tears. And what you're also doing is you're screwing up so tightly that you're closing the duct that normally your tears would come out of to moisturise the front of your eye. So you're actually producing a bit more tears by that pressure of closing your eyes, and you're not letting any of them out as well because you're closing your eyes so tightly. So when you open them up again, you actually have sort of eyes that
so it's like standing on the plug hole in the shower, so it stops it draining.
Yes.
So you get a build up.
Yes, that's right. That could
so
be why it is.
There you go, Andreas. That's why when
Thanks
you yawn in your science lessons at school, that's why your
yawning
eyes
now.
Mike is in Beatley. Hi, Mike.
Good.
Welcome to the Naked Scientist. What would you like to talk about?
Yeah, good evening to you. Yes, I spoke storms, thunderstorms, lightning, mainly in the question of. I heard this gentleman had a nasty ordeal by a lightning strike. Nasty that. And but no, the thing with the lightning, I always thought it's a negative charge in the cloud and a positive to the earth, isn't it?
Yes, you're right. That's spot on.
As lightning comes down from the cloud, as it gets towards the earth, I always thought it goes from the positive from the earth goes up to meet the actual negative charge.
Yes, that's also true, because like charges do repel and unlike charges attract. So you get a negative bottom to the cloud, and this encourages the ground to become positive underneath. And the reason it does that is that all the negative in the ground moves away, leaving just the plus behind. So the ground goes plus, the cloud goes minus, and when you've got a strong enough electric field, it overcomes the natural resistance of the air, and it discharges, and it comes down a very fine thread. Your average thunderbolt is about the size of a 5p piece, so very, very small, about a centimetre across.
Yeah, amazing. I didn't realise that's only that amount, but that looks rather large. That would be obviously the positive going back up, wouldn't it?
Well, traditionally, when we talk about electricity flowing, we're talking about electrical charges, which are electrons moving down from an area where there are lots of electrons to an area where there are fewer. And that usually means going from minus to plus, because there are lots of electrons at the minus and fewer at the plus. And so you get this charge spreading down. Once you've actually ionised the air with this, what's going to become your lightning strike, then you get a very high current for about a fraction of a second, very, very short space of time. You get about 30,000 amps of current flowing down this lightning spindle towards the ground. And it imparts something like 1 to 10 billion joules of energy. So there's a lot of energy.
Yeah.
In fact, I might as well. In fact, I can share this with you, Mike, because I've got a question here from Andy John, who said, "Can you harness the electricity in lightning?" So I thought I'd look up some lightning facts, and in fact, there are 2,000 thunderstorms going on at any time all around the Earth, which equates to about 100 strikes every single second. But the average lightning strike, which is 3 miles long, unleashes the same energy as 1 million tons of a ton of TNT. So it's a pretty whacking great smash.
Certainly is.
But the energy, if you do the simple sums, the energy in your lightning bolt, let's say it's 1 billion joules of energy. If you look at a 100-watt light bulb, because I guess if you're asking can we harness electricity in lightning, you're asking could we do something useful with it? Well, let's look at how much energy there is in real terms. A 100-watt light bulb burns off about 100 joules of energy every second. So that equates to 100 times 3,600 joules in an hour, because there are 3,600 seconds in an hour. So that's about, and if you times that by 24, that's about 9 million joules of energy in a day to run a 100-watt light bulb. So how long could you run a 100-watt light bulb with the energy in a lightning bolt?
Good question.
Yeah, well, the answer is if you divide the 1 billion joules of energy in a lightning bolt by the 9 million joules it takes to run a light bulb every day, it's about 100 days. Which doesn't, it's not much, is it? Just one light bulb for 100 days with all that energy in a lightning bolt.
Power that, yeah. But that's an interesting fact. And also because what I was just saying, that gentleman who was struck by lightning, he was obviously thrown. So would that power from the charge coming up would have lifted him off the ground, or anyone who as long as they didn't hold anything to earth themselves, everyone would be just lifted off the ground?
No, you're on. It's an interesting observation that he moved. The reason he moved was because of his own muscles. This is called opisthotonus, and this is sudden catastrophic muscle contraction. And when you have all of this electricity running through your body, muscles are electrical. So a big bolt of lightning is a big discharge of energy which triggers all of your muscles to think that the nerves that supply them have told them to contract. So all your body's muscles contract at once, and this can include the heart, and it can obviously stop your your heart, or it can put your heart into a funny rhythm. So all the muscles contract at once. The strongest muscles in the body are the ones that hold you standing upright, because they have to hold you upright.
Your legs muscles.
And so what you do is the world's biggest high jump, as soon as you're hit by the lightning, and it throws you in whatever direction you happen to be pointing at the time. And that's why people who have electric shocks generally get thrown over. It's their own muscles bowling them over. It's nothing to do with the electricity moving through them, apart from activating their muscles.
Well, that explains something to me, because I thought that was the actual charge, but it's not. It's like you say, it's the muscles then.
Not quite. But anyway, thank you very much, Mike. It's great having you on the programme.
Right, yeah, thank you very much for answering the question.
It's a pleasure.
Thank you. Yep,
Take care.
I will. Yeah, thanks. Bye for now.
Helen, got a quick one here from Will, who says, Dear Naked Scientists, which is the best way for me to boil my tea, water for my tea, on an electric stove or in a microwave?
Of course, there's very many answers to the question in terms of what you mean by better, but we've decided here at The Naked Scientist that the microwave method actually might be quite dangerous. You've had a go at this, haven't you, Chris?
Yes, we did have a go, but we did it for scientific reasons.
Absolutely, but it's all about the waveform that microwaves form inside of your microwave, and they can actually basically concentrate in certain areas, and what it can do is superheat pockets of water inside your teacup or whatever it is you're boiling to just huge hundreds of degrees, much more than you might imagine, but it's being held in by the water molecules around it so that it doesn't actually evaporate. So when you take that cup out of the microwave and you stir it perhaps with your teaspoon, you might be letting out through the conductive metal of your teaspoon, you might letting those superheated pockets of water out, and it will explode. Suddenly it'll do what it's meant to do, which is expand, and it could be catastrophic, covering you in boiling water. So I think stick to the stove, or maybe under very controlled scientific conditions, have an experiment with it, but cover yourself up and be very careful. But
got a very quick one here from Paul, who says, Hi there, Naked Scientists. I'm listening to you in Hong Kong. I listen to you on your podcast, and what a fabulous show it is. The topics are varied and interesting, and you all have unique and enjoyable personalities. I guess it's referring to your shining, glittering personality,
thanks.
Helen. He says, you've made my iPod purchase pay back several times, especially if it gets hit by lightning.
Watch out.
No, he says, it's a really interesting question, this. He says, I find that when I clean the earwax from my ears using a Q-tip, naughty, you should never stick things in your ears.
No.
I tend to feel an urge to cough. Is this a common reflex? Am I somehow pressing on a coughing nerve with the Q-tip? And if so, is it a data point in support of reflexology or acupuncture, or am I just a freak?
I've never heard of this, and I certainly don't experience it myself.
No, I was intrigued, actually, because I do know quite a bit about the anatomy of the head and neck from medical school days, and I'd not heard of this, but I looked it up, and there is a cough-ear reflex.
No.
But get this, Paul is very, very rare. Only 2.3% of the population actually experience this. There's something called Arnold's nerve. It's part of the vagus nerve, which supplies the head and neck, and it supplies the back and lower floor of your external auditory canal, the tube where you stick your finger towards your ear. And if you stimulate it, it can provoke a coughing reflex. But as I say, only about 2.3% of people get it on one side of their head, and only 0.6% of people that they've looked at have it on both sides of their head. So very, very rare indeed.
Absolutely special. I've got a very quick question here from Adam Little in Tennessee in the United States. Thanks for writing to us, Adam. That's great. He says, when I ride a lawnmower, it vibrates a lot. And when I get off, well, I hope it does. Obviously, it's doing its job. But when he gets off, his feet feel like they're vibrating, even though the ground below me isn't vibrating. And why is that? I get a similar feeling when I get off my rollerblades. What do you reckon, Chris?
The answer to this is it's all about how your body processes incoming sensory information, because we have this process called adaptation, where if you have something happening to you all the time, the nervous system shuts off its sensitivity to that thing to avoid sensory overload. So, for instance, if you go around someone's house, often when you walk into their house, you'll notice that it smells funny. Have you noticed as you go in other people's houses? Not just your house, which is very stinky, but other people's houses do smell a bit funny. And then after you've been there a few minutes, you stop noticing, don't you? Well, that's because the nervous system has this process of adaptation where it switches off its sensitivity to things that are there continuously to stop you having sensory overload. Our bodies are only interested in things that change. So, for instance, if you were in the jungle and you were at risk of a fire, you might get burned alive. The smell of smoke suddenly cropping up, you need to pay a lot of attention to that. But the smell of all the trees around you isn't changing, so your body's not so interested in it. So the answer to this question is that when you're on your lawnmower, the vibration is there all the time. So the body suppresses its sensitivity to it. But then, when you take the vibration away, the thing the body's suppressing, now you've got sort of gone the other way. You're suppressing something that isn't there, so your body's saying, well, what is this thing that I'm suppressing? So you start to invent the signal that you're trying to suppress. So it's almost like if you say you've got +1 and you take 1 away, it goes to 0. But if you take the 1 away, you then go to -1. And so what you're sensing is the inverse, the reverse of what you were trying to cancel out. So it's sort of the sensory system cancelling out what was there.
It's
and it's the same.
Trick of the mind.
It's sort of the same thing when you go on a boat or an aeroplane for a long time. You get back on dry land, and you've still got sea legs.
Yeah, I get quite land sick sometimes if I've spent a long time at sea. So anyway, we are still waiting for your answers to our question of the week, our teaser question, that is. The question of the week comes up a little bit later. But we're asking you this week, how many tons of prehistoric plant matter were compressed and squashed under the earth to create every gallon of petrol that we use to zoom around in our cars?
The Naked Scientist Podcast, brought to you by thenakedscientist.com.
Jerry Woodall joins us now because biodiesel is one option for powering cars in the future, but another fuel we could use is hydrogen. And this has the benefit of producing only water when it burns, so it should in theory be a lot cleaner, but it can be very expensive and it can be quite dangerous to extract it and store it. So what Jerry Woodall has done, as well as inventing in his past the LED, is come up with a way to make lots of hydrogen on demand and safely so we can power cars with it. Hello, Jerry.
Hi, how you doing?
I'm very well, thank you. Thank you for joining us on The Naked Scientist. So,
my pleasure.
Tell us about this new way that you've come up with to make lots of hydrogen.
Okay, so it's a form. We use aluminum as our high energy content material. Aluminum, like oil, has a very high energy content. The only difference is that aluminum will form an oxide skin, so you can't use it for that purpose. Whereas oil, has all these stable hydrogen-carbon bonds, and it just sits there in the earth until you're ready to burn it.
But when you say you can't use aluminium in that way, you're talking about using it exactly how?
Well, if I want to take the aluminum and use it to split water into hydrogen and oxygen and have the aluminum grab the oxygen, a piece of aluminum sitting on the shelf won't do it because it has a passivating oxide already on it. So the aluminum, if we had a piece of aluminum with no oxide on it, it would readily split water.
And so how do you propose to do that? Because you have to go through quite a lot of chemical steps normally to strip that protective oxide skin off,
correct.
Don't you?
So this idea of using aluminum has been around a long time. There are no less than 26 patents in the literature since 2001 of mechanical scrapings, aluminum powder, and all these sort of things. They're okay, but they're not very practical. What I discovered that is if I added the element gallium, which is a group 3 element in the periodic table, that gallium in the aluminum prevents the aluminum oxide from passivating it. So when you do that and make an alloy, chunks or particles or pellets, this material will when it comes in contact with water, will split the water, liberating the hydrogen and forming an aluminum oxide powder.
But you don't end up with a skin on the aluminium. The gallium seems to stop it somehow.
That's how it does it.
Do you know how?
So the gallium prevents the passivating oxide from forming on solid aluminum.
But do you know how? And how did you discover that?
Yes. So the first experiment I did back in 1967 when I was still at IBM, it turns out I discovered this by having a liquid of gallium and aluminum. Gallium melts just above room temperature. So I was working on a material, a semiconductor material called actually gallium aluminum arsenide. And what I discovered is that when I had these melts that I used to grow the crystals from, which was mostly gallium and aluminum, if I added water to that, I would get hydrogen coming off in a big way, boom, boom. And so then I sat down and figured it out. So it turns out if you're aluminum in a liquid pool of gallium, there is no solid oxide protecting you from further reactions. So a water molecule comes along, the aluminum sees it, and splits it into hydrogen and oxygen.
So how would you see this being used practically in a car, for example, and why would it be better than just having a cylinder of hydrogen sitting in the back of the car?
Oh, because it's hydrogen on demand. So aluminum is safe by itself. The aluminum-gallium alloy is safe by itself. So I can drive around. If I had a collision, God forbid, nothing would happen.
But you would see this being used. How would the engine get the hydrogen in the right amount?
Oh, very simple. I would have a pile of a bunch of aluminum in my aluminum tank, if you will, and then I would feed water into it or feed it into a pool of gallium, and then I would add water, and that hydrogen comes off and then goes into your intake manifold, just like BMW uses
And
BMW
how many? I don't suppose you can say miles to the gallon, but how far could you travel on how much aluminium? Is this viable?
Okay, so I need to drive a car the size of a U.S. Taurus, 350 miles. You need about 18 gallons of gasoline. Okay, I would need 320 pounds of aluminum to drive the same distance using an internal combustion engine.
So it's actually quite practical. This could be done.
Yes, it's economically practical right now. Also.
What about getting the aluminium back at the end? What are the waste products and recycling, that kind of thing? How could you complete the loop and make sure it's clean?
All right. This is very important that your readers and listeners understand this. You don't get this for free. We get all those dinosaurs from a long time ago, so we take them out of the ground for free as oil, right? And we can't grow them back again. But aluminum doesn't exist as pure aluminum. It exists as aluminum oxide. So once I've finished using the aluminum up to create my hydrogen, I have to get it back to aluminum again. Now, the major aluminum companies, the factories, take the aluminum oxide that they dig out of the ground, pass electricity through it, and get it back to aluminum. So you have to do that to get the fuel back again.
What about the gallium? Can you recycle that?
Yes, the gallium is totally inert. It's completely reusable. So you can use it over and over again. It does not react. It's like a catalyst.
Brilliant. So you could envisage, just to sort of summarise all that, you could envisage making these gallium aluminium pellets. You put water onto them, react it to make the hydrogen. You get aluminium oxide and gallium back. You then clean that up and pass electricity through it in a power station, say a nuclear power station or a wind or tidal power station, to make sure that it's carbon neutral. So you've got clean energy, and this is a way in which you could power the planet.
That's correct. It's very green, and you need to point out to your listeners, however, if you're not interested in making hydrogen, what I'm doing should not be of interest. I mean, people have asked me, well, if it takes energy to get aluminum back out of aluminum oxide, why not just use the electricity itself? Well, you got to get the electricity from someplace, either a coal-fired plant or something. That leaves a carbon footprint. So if you are willing to use hydrogen, which is very clean and green, as you said earlier in the program, if you're using a fuel cell or an internal combustion engine, the reaction product is just plain old water. You can sniff it. It won't hurt you. You can use it in your house. So the point is, this could be a very viable solution. There's enough aluminum and gallium on the planet's surface to run 1 billion cars continuously.
Well, that's encouraging, isn't it? Jerry, thank you very much for joining us on The Naked Scientist.
Okay, thank you.
That's Jerry Woodall from Purdue University, who also, his claim to fame is he invented the red LED, the thing you see on your video recorder and all those other gadgets. That was him who made it.
There you go, a polymath indeed. And now we have a story that should appeal to any would-be environmentalists with a sweet tooth. And that's because scientists have sussed out how to turn fructose, or one of those types of sugar, into fuel that could rival the power of petrol. Chris went to speak to Miss Wisconsin-Madison's Jim Domesic.
The basic idea that we had was to try to convert carbohydrates into liquid transportation fuels, and to compare what we could make by chemical catalysis with what is currently made by fermentation, that is ethanol.
So what's actually wrong with ethanol then, Jim? Why can't we use that?
Ethanol has certain disadvantages as a fuel. It has a relatively low energy density, so the energy per liter of ethanol is about 30% lower than that of standard petroleum, gasoline, or diesel. Also, ethanol has a bit of a high volatility, and it tends to boil off in hotter weather, so an ideal fuel would have a little bit lower volatility than ethanol. And finally, ethanol loves water, and therefore it tends to be hygroscopic, leading to absorption of water into your gasoline, which is undesirable. So we were looking for routes to make other fuels that would alleviate these potential problems that ethanol has.
And what did you come up with?
Well, we came up with this compound called dimethylfuran, DMF. So if you start with a molecule of a sugar like glucose, or in our case, fructose, it has 6 carbons and 6 oxygens. It turns out if you remove 5 out of the 6 oxygens, you end up with this dimethylfuran, and it actually has all of the desirable properties you'd look for in a fuel. That is, it has a energy density that's very similar to petroleum. It has a volatility that's a little bit lower than ethanol, which is good. And it also is hydrophobic, meaning it does not like water. which is the same as petroleum.
Now, how easy is it to actually do this, though? Do you actually get more energy out than you have to put in the synthesis?
Well, we have a two-step process. In the first step, we remove 3 oxygens by removing 3 water molecules from the sugar, which leads to a chemical intermediate called hydroxymethylfurfural, HMF. That process does not theoretically require energy. And then in the second step, we pass hydrogen over this HMF and remove 2 of the oxygens, which gives us dimethylfuran, which has 1 oxygen. Now, we do this all in a solvent, and at the end of the process, we have to evaporate the solvent to make the fuel. However, the solvent we use is an organic solvent, and compared to the production of ethanol by fermentation, where water is the solvent, the energy required to evaporate the organic solvent is about 1/3 of the energy required to evaporate the water. So potentially, this is a energetically favorable process for making the fuel.
And I guess that because there's so much in the way of raw materials, such as sugars, which are chucked out by plants, such as the sugar industry, the chocolate industry, there must be no shortage of raw materials from which you can make this stuff.
Well, that's the hope. If you look at biomass, over 75% of biomass are sugars. I do point out, though, that the major sugar in biomass, for example, lignocellulosics, which is the main form, is glucose. Our process works primarily with fructose, so that there is a biological step involved in converting the glucose into fructose. Once you have the fructose, our process works pretty well to make the dimethylfuran.
Well, let's look at actually how you could use this. So will it burn and behave in an analogous way to petrol? Because that must be a key question.
Yeah, there was a discussion in the literature on this. In the 1980s, people went through and measured the octane number of DMF, and it turns out the octane number is something like around 120, which is a very, very good octane. So dimethylfuran should be a very, very good burning fuel if you can make it efficiently from biomass.
And what about the cleanness of that burn? Will it produce lots of nasty organic residues, which, rather like diesel, it has a very poor press on this, are going to trigger respiratory problems, or will it burn clean?
Combustion people I've talked to here at the Engine Center of Wisconsin, their suggestion is that it should burn cleanly. But there have not been many studies of this in the past because there has not been a lot of dimethylfuran available. I think now, opening the possibility of DMF as a fuel, that would be interesting to study.
So say you manage to pull that off and it does perform well as a fuel, engines will tolerate it, it won't corrode them and things like that. Is the process to make it actually scalable? Can we get reasonable amounts of this that you could see then turning up at the petrol pump?
Yeah, the process should be scalable because if you look at the steps that we use in our two-step process, they're very similar to the kinds of processes that are currently used in the petrochemical industry. Therefore, they potentially should be scalable.
And so, presumably, you'll be doing some tests on this to try and get this running into engines pretty soon and see how it behaves.
Yeah, that's the next step on our process, actually, is to scale it up so that we can make amounts of DMF that are now suitable for engine tests. That is, in fact, one of our short-term goals.
That was Jim Domesic talking to Chris about extracting a new fuel from sugary fructose.
Laying the facts bare, The Naked Scientists.
Now, John in Colchester got in touch with us and said, would it be possible to run anything on 100% biodiesel, or is it too pure? Well, I've told Azzy about that, so she's over in Bath at the moment and they're making some biodiesel for us, so hopefully we'll find out the answer to that one on the way. But right now, let's welcome from Cambridge University, David Mackay. Hi, David.
Hi.
Thank you for coming in. Now, we've heard a lot of options on today's programme about things that you can do to live a cleaner, greener, meaner life. Is there a scientific argument for adopting these approaches?
Well, it's definitely exciting to have these options of fuels like hydrogen and other fuels derived from biomass. But an important thing to think about is the actual energy. Where is the energy coming from? And it isn't that we've got a fuel problem. If we want to get off fossil fuels, it's not so much fuels, it's where we're going to get the energy from instead of from fossil fuels. So I've done a little calculation like your lightning strike calculation, just adding up the numbers for Britain. Could we live on our own biofuels, for example? So we start with sunlight, which is 1,000 watts per square metre at midday. And then, it's not midday all the time, so we lose out at night time, and in evening and morning, it comes down to 250 watts per square metre on average. That's if there's no clouds, but it's cloudy 2/3 of the time, so we're down to 80 watts per square metre. And that's the figure if you're at the equator. We're quite far north. It comes down to 50 watts per square metre on average is the power of sunlight. And then the best plants for making carbohydrates out of are 1% efficient. So that gets us down to half of a watt per square metre. And now you just need to know what's the population density of Britain. It's 4,000 square metres per person.
Okay.
And if I get to be dictator of Britain, I say, OK, let's have 75% of Britain devoted to growing biofuels. How much energy do we get from that? Well, the raw carbohydrate that you're getting out in the form of plant material is 36 kilowatt hours per day. And in Britain, 36 kilowatt hours per day is pretty much the amount of energy we're spending on transport at the moment. But you've got to bear in mind we haven't processed that plant material into fuel.
So in other words, if we put across all of the space we have available, we could just about be energy self-sufficient using plants. But what about food? We're not going to eat. We're going to buy it all in from France or something.
Yeah, earlier on your show you were saying we could live on organic food. But that organic food needs that land to be grown on as well. So we really have a crunch. And also bear in mind the biofuels, we hadn't actually produced the biofuels, and producing biofuels from that plant material requires energy too. And many of these biofuel processes lose a lot of energy along the way, have to put in extra energy.
So when we've got President Bush saying we're going to put across X amount of land to growing all these things to make biofuels, there's not a sound either ecological or scientific argument for doing that.
Well, the population density of America is lower than ours, so I'd certainly say Britain can't live on biofuels for transport in the way that we currently live. America, their population density is maybe 5 times lower than ours, so they've got a
still got to eat, haven't they? They've still got to eat food.
Yeah, and I do think there's a big worry that in this rush to look green, people will actually end up doing something that's actually very bad for the poorer people of the world who would like to use the land for food rather than for our biofuel.
Also, is there a risk that if you suddenly switch all this land away from agriculture, you may actually make the environment worse because you're establishing even more of a monoculture? You've got lots of one particular kind of crop growing to make lots of oil, which we can turn into biodiesel or whatever, and that could have knock-on effects for the environment.
Yes, that's right. And another environmental concern is the water requirements. If we did take over lots of extra land and start growing more crops on it, we'll end up with a world water shortage as well.
So what is the answer then? Just we travel less? What do we do to get around the problem?
I think we need to be looking at lifestyle changes to be able to live self-sufficiently on our own renewables. Alternatively, we need to be really nice to other countries and say, OK, Libya, you guys, you've got a nice low population density, you've got lots of sunlight, please could we be nice to you and buy a bit of solar power from you?
I did a back-of-the-envelope calculation and found that if you covered the entire Sahara Desert in solar cells, assuming they're about 30% efficient and the sun shines for 12 hours of the day, then you could generate about 10 to the 15 watts. I mean, that's the equivalent power of the Gulf Stream. That's a lot of energy. I mean, that's a million gigawatt nuclear power stations, for example, or Gulfide, whatever power station, a million gigawatt power stations. It's a lot of energy. Why aren't we doing this? This surely should be the answer.
I completely agree. I think solar in the desert is one of the options for humanity. You could certainly power Europe and North Africa all at a European standard of living using just a small fraction of the Sahara Desert. Why aren't we doing that? Well, why are we bombing Iraq?
Don't go there. Well, I suppose we could have said that for President Bush. But to sort of wrap up then, how sound is it to say to people, oh, everything makes a difference? Turning off your TV when it's on standby, not leaving your phone charger plugged in when it's not charging anything, this will help to save the planet. Will it?
Some of these things definitely make a difference. The phone charger is crazy. If you take a typical Nokia phone charger, it's using less than 1 watt. It's a really tiny trickle. It's probably about 1% of 1% of your energy consumption is going into the phone charger. So a phone charger...
But the argument is that there are so many people with these things plugged in not doing anything that, en masse, if you add them all up, it makes a huge difference.
If you add it all up, you get 1% of 1% of the UK's energy consumption, and that's how big a difference the phone charger makes.
So we're being penny wise, pound foolish with that argument, is what you're saying?
I think so, but there are other things on standby that really do make a difference. If you're leaving a computer plugged in all the time, that's using maybe 80 watts. If its screen is switched on, that's another 100 watts maybe. A laser printer just sitting doing nothing at all, that's 17 watts. And all of these things really do add up. And that if everyone were careful in switching off those sort of devices, you could be saving maybe 10-20% of our electricity consumption.
Thank you very much. That's David Mackay, who is from the University of Cambridge.
Now, last week's question of the week was about the shape of black holes, and our expert astronomer royal, Lord Rees, told us that while a stationary black hole would be spherical, they can be pulled out into a disc shape if they're spinning. Now, we've had a couple more emails on this one, including Don Jennings, who has said that a black hole does not exactly have a shape, but its event horizon may. The event horizon is that point of no return for a black hole. We've also heard from Jussie Dittmer, who said that black holes can be imagined as a point in space that has gravity. Sadly for the Naked Scientist, Sabina Miknovitz has left us, but to pursue her dream of clambering about on volcanoes. Mad girl, but yes, very exciting. So here to present this week's question of the week is Diana O'Carroll.
Hello and welcome to Question of the Week. On this edition, Michael from Houston wants to know about the behaviour of our canine friends when it's time for walkies.
Hi, my name is Michael Rashty. I'm calling from Houston, Texas, and I'm calling to find out what dogs are doing when they're lifting their legs. Are they targeting a particular spot? Are they aiming to cover up another dog set? Do they recognize their own scent? And how do you know?
One mysterious emailer, known only as Templeton, came up with this answer.
I suspect that when a dog pees on a landmark, it's actually marking its territory with the scent that other dogs can smell. They might also be doing it to advertise their fertility.
Senior lecturer in animal behaviour at Anglia Ruskin University, Dr. Charlotte Neverson is our expert with the solution this week.
First of all, only males tend to do this leg-cocking behaviour. Females tend to squat. Now, this difference in posture may actually be important because the placement of the marks might make them mean different things. So why do male dogs actually cock their legs? Well, of course, they could just be relieving themselves, but as many owners and also many scientists studying animal behaviours think, they might be scent marking. If we look back to the wolf, which are the closest genetic ancestors to dogs, there is some evidence that these scent marks play a role in establishing territories and defending them against intruders. So they're effectively saying, I'm here, I'm great, and don't mess with me. Wolves also live in packs, so it may be used in intergroup communication. So how can we take this back to the domestic dog? Well, domestic dogs now, of course, live with humans, so they don't actually need to defend areas in parks, and they may only go there from time to time anyway. A lot of dogs are also neutered, which affects their hormone levels and might also change the reasons why they actually might want to mark. So it could be that leg-cocking behaviour may not actually mean anything. But observations suggest that dogs are still interested in each other's marks and also in each other's bottoms. So it could just be the modern pacifist dog saying hello to each other.
Although cheaper than title deeds, the Naked Scientists do not recommend using territorial marking to acquire Buckingham Palace. It's probably also not the best way to leave a hello message for your neighbour. Next week, we have a question from Wasim in Oman.
What is the physics behind the way sycamore seeds float like helicopters, and why?
Do you know why this is the case? Or is there something you've always wanted to know the answer to? Send us an email to questionoftheweek@thenakedscientist.com. That's all from Question of the Week. Back to the studio.
Thanks, Diana. So if you think you know the physics behind the spin of those lovely sycamore seeds as they drop down from the trees, then do drop us a line at questionoftheweek@thenakedscientist.com.
Well, it's time now to head back to Azzy at the University of Bath, where they'll be making us some biodiesel.
Hello, welcome back to Kitchen Science. I'm still at the chemistry department in the University of Bath with Chris and Matt, and we have biodiesel being made in the fume hood here, and the vegetable oil looks really clear and it's swirling around in the little flask. So Chris, what's going on?
Well, the vegetable oil completely changed to biodiesel, and we're just going to work that up by pouring it in a conical flask and then pouring water on top, and that water will take away the glycerol, take away any excess methanol, and just leave us with our biodiesel on top, like if you poured oil into water.
Okay, so you've just poured it into the flask, and here goes some water.
So we can tap off the biodiesel from the top.
All right, well, we've got our biodiesel. We are now going to run over to the engineering department and test it out. Okay, so we're now navigating the depths of the engineering department, and we're about to test our biofuel. Hello.
Right then. My name is Gary Hawley, Professor of Automotive Engineering here in the Department of Mechanical Engineering at the University of Bath.
You've got this huge white van in this lab.
Well, where we are now, we're in the Vehicle Research Laboratory.
We've brought some biodiesel along with us, so what are we going to do now?
Right, well, what we've got here is pure biodiesel, 100%, but unfortunately, the motor manufacturers in Europe will only guarantee the vehicle if it's got a B5 blend. That means 5% of the fuel will be biodiesel and 95% will be ordinary forecourt diesel. So we're going to run the biodiesel in a B5 blend through the vehicle, and we're going to see how it reacts. Right, we're just going to start the tests now, and what's happening now is the driver is driving the vehicle on a rolling road, so the wheels are going round, but the vehicle's not going anywhere because it's strapped down.
That looks like the car is running in the gym.
That's exactly what it is. It's just like if you were on a running machine in a gym, you run on the conveyor belt. In this particular case, we have a roller going round, so the wheels are turning the roller, and then the roller is absorbing the load. We're measuring emissions, that's oxides of nitrogen, we're measuring carbon monoxide, we're measuring CO2, and we're measuring unburnt hydrocarbons. Altogether, we're taking somewhere in the region of about 15 dependent signals from the vehicle. What we'll do now is we'll go up into the control room and we'll be able to see real-time comparing what's happening with this B5 blend and what we did previously when it was just 100% forecourt diesel.
All right, so we're just off to the control room now. Loads of computers in this room. Okay, so what do we get?
Well, the first thing I'm going to do is to look at the vehicle performance. We can see here on the screen that there are no adverse effects on performance from using the actual biodiesel blend. So the next thing we're going to have a look at is the fuel consumption. And we can see that the fuel consumption, it is about the same. There's a little bit of this discrepancy in favour of the 100% forecourt diesel. But then again, if we now look at the emissions, we can see that the engine does appear to be running cleaner, and that's because of the clean properties of the biodiesel itself, due to the fact that it does contain an amount of oxygen which helps to improve the cleanliness of the burning the combustion chamber. So all in all, we've got no adverse effects on performance. Fuel consumption is about the same, and the emissions are fractionally improved.
But there doesn't seem to be much difference between them. So where is the advantage in using this 5% blend?
Well, the biodiesel itself has come from a renewable source. So you could actually say that taking everything into account, the cultivation of the plants and turning the crops into oil and then turning the oil into a fuel, that 5% of it is approaching carbon neutrality.
Okay, folks, so there you go, 5% biodiesel in your normal diesel is a little better for the environment. And yes, you can make fuel out of vegetable oil. So there, back to you guys.
Thanks, Azzy. So there you go, biodiesel made in front of your very ears here on The Naked Scientist. And there are more great Naked Scientist experiments, including some you can try at home, on our website. That's at nakedscientist.com/kitchen science.
And now the answer to this week's teaser question. We asked you what weight of prehistoric plant material must have gone into producing every gallon of petrol we burn. We had the correct answer from Jim in Holcombe. Thank you so much for your answer, which is 98 tonnes. And that's the equivalent of shoveling 40 acres of wheat into your tank every 20 or 30 miles.
The other shocking thing about that is that in the last 200 years, we've burned off 13,000 years' worth of plant growth on the Earth, just in terms of the fuels we consume. We're coming up towards the end this week. I've got an email here from Andrew Hewson, who is listening to us in Poole in Dorset. He says, "Hi, just listening to the programme over the internet. I heard comments about hot spots being generated in a liquid when it's heated in a microwave oven. I thought this was only a problem in those ovens where there's no rotating turntable for the cooking container to sit on." That's true, Andrew. To a certain extent, the microwave turntable does keep the food migrating through what's called the standing wave pattern in the microwave. Thing is, though, for some reason, us humans love doing things symmetrically. Everyone puts food straight into the microwave, or drink, so it sits right on the middle of the turntable and then spins in a nice perfect circle. And this still means you can get hot spots in the middle of whatever you're trying to heat up. best way to microwave something, if it's small enough, is to actually move it to one side of the turntable, because then it goes through many of these standing wave points, and this means the food gets much more evenly heated. So, little cooking tip of the day from the Naked Scientists. Anyway, that's it for this week. Thank you very much for listening. We really appreciate your emails. Please keep them coming. Also, if you like the show, do please write us a review on iTunes or Podcast Alley, because we're looking a little bit thin on the ground there. Now, to next week. And we're taking the body to extremes, it seems, because we'll be finding out how we handle high altitude, finding out how deep we can dive, both with and without oxygen, and also how fighter pilots can handle the G-forces that are inflicted on them by high-powered jets. So if you have any questions on any of that, then send them to me now, chris@nakedscientists.com. And don't forget, there's more science from us, which is available from the Nature podcast. That's at nature.com/nature/podcast. And also, there's lots of fun and funky science discussion going on our forum at the Naked Scientists website. That's nakedscientists.com/forum. Thank you very much to our production team this week: Ben Valsler, Azzy Katiri, Petro Minch, and Diana O'Carroll. Have a great week and see you next time.